Traveller, you didn't arrive here by accident. Something in the quiet machinery of the cosmos guided you here, as if the universe set a gentle hand on your shoulder and whispered for you to listen. Picture Earth trembling with a magnitude 7.8 release, while just 3 days earlier a G3 geomagnetic storm swept across our magnetosphere like an invisible tide. What are the odds that two forces so different would strike within the same breath of cosmic time, and behind them, drifting silently toward the sun, an interstellar wanderer with a coma nearly half the star's diameter, a structure vast enough to swallow dozens of Earths without touching the sides? What if none of this is coincidence at all, but the beginning of a deeper pattern we're only now learning to see? Let's drift a little deeper. On September 18th, 2025, at precisely 14:55 from TNT, UTC, a fault deep beneath Russia's Kamchatka Peninsula, released decades worth of accumulated tectonic stress. In under 3 minutes, the Earth discharged energy equivalent to 32 billion tons of TNT, forceful enough to shorten the length of Earth's day by measurable microseconds. While imperceptible to human senses, that subtle shift served as a reminder of the planet's dynamic interior, one that stores stress patiently, then releases it without warning when internal thresholds are exceeded. The rupture triggered a cascade of alerts across the Pacific. The DART tsunami network scattered across the ocean floor registered pressure anomalies as waves radiated outward at nearly 800 km/h. NASA's JASON satellites confirmed open ocean wave heights exceeding 3 meters, energetic enough to damage coastal infrastructure thousands of kilometers away. Observationally, nothing in this sequence violated known geophysical principles. Kamchatka sits atop a classic subduction zone, where the Pacific Plate dives beneath the Yakutsk Plate at approximately 8 centimeters per year. This slow convergence builds stress along a gently dipping megathrust fault, capable of producing some of the largest earthquakes on Earth. The July 29th Earth magnitude 8.8 event had already destabilized the region. Additional large aftershocks were not only plausible but statistically expected. Yet the timing of the September 18th earthquake raised questions that extend beyond conventional tectonics. Just 3 days earlier, Earth had experienced a G3 geomagnetic storm, one of the strongest of the year. Unlike the sudden, dramatic arrival of a coronal mass ejection, this disturbance originated from a high-speed solar wind stream, emerging from a persistent coronal hole and opening in the Sun's magnetic structure, where charged particles escape freely into space. Solar wind speeds approach 700 kilowatts, while particle densities dropped below 1 proton per cubic centimeter, creating what space physicists describe as a solar wind vacuum, a low-density regime far more extreme than any vacuum humans can generate on Earth. Geomagnetic storms of this type induce widespread fluctuations in Earth's magnetosphere. Ground-based magnetometers recorded sustained magnetic disturbances for nearly 48 hours, while electrical currents known as telluric currents were induced within Earth's crust. These currents follow conductive pathways such as fault zones, sedimentary basins, and mineral-rich formations. Although widely recognized for their effects on power grids and pipelines, their potential influence on tectonic processes remains a subject of ongoing scientific debate. The dominant seismological perspective maintains that earthquakes are governed primarily by mechanical forces, the accumulation and transfer of stress along faults due to plate motion. According to this view, the September 18th magnitude 7.8 event fits neatly within the expected aftershock distribution for a megathrust rupture of the July 29th scale. Stress redistribution calculated through Coulomb modelling revealed enhanced failure probabilities along several nearby fault segments. From this standpoint, the temporal proximity between the geomagnetic storm and the earthquake remains an interesting but ultimately coincidental overlap. However, a minority of researchers have explored whether geomagnetic disturbances might influence the timing of earthquakes already close to failure. The hypotheses do not challenge plate tectonics, but propose that electromagnetic or atmospheric perturbations could act as triggers advancing the timing of an inevitable event by hours or days. Proposed mechanisms include changes in pore fluid pressure due to induced electric currents, ionospheric heating altering atmospheric load, or electromagnetic modulation of fault friction. Importantly, these mechanisms cannot generate earthquakes. Independently, they could only act on faults that are already critically stressed. Kamchatka in September 2025 met this criterion. The July 29th megathrust rupture had transferred stress across a rupture zone extending nearly 600 kilometers. Over 40 aftershocks above magnitude 6 occurred between late July and mid-September, indicating a region in active adjustment. Against this backdrop, the coincidence of a strong geomagnetic storm and a major aftershock invites scrutiny, not because it overturns tectonic theory, but because it highlights how little is understood about the potential coupling between Earth's electromagnetic and mechanical systems. Complicating the picture further is the presence of an unusual celestial participant. During September 2025, Earth was not the only body responding to increased solar activity. An interstellar object, 3I Atlas, was approaching the inner solar system. Unlike typical comets, which begin sublimation near the orbit of Jupiter 3I Atlas, showed early and vigorous activity at distances where solar heating should be negligible. Observations from the Hubble Space Telescope revealed a coma approximately 700,000 kilometers across nearly half the diameter of the Sun. This made 3I Atlas a massive electrically active plasma structure, moving through the solar wind at a time when the Sun itself was approaching peak activity in solar cycle 25. While the interstellar visitor played no direct role in terrestrial events, its presence contributed to a broader context in which solar magnetospheric and tectonic systems simultaneously displayed heightened activity. The convergence of these domains, solar wind anomalies, geomagnetic storms, seismic clusters, and interstellar plasma dynamics, created an atmosphere of scientific curiosity and philosophical reflection. The Earth's crust does not respond to cosmic influences with agency or intention, yet it remains an open question whether external electromagnetic conditions can subtly influence the timing of tectonic processes under specific conditions. Scientific skepticism is warranted. Extraordinary claims require extraordinary evidence. Still, the September sequence reminds us that Earth exists not as an isolated system, but as a node within a dynamic heliospheric environment shaped by the Sun, by space weather, and occasionally by visitors from beyond our solar system. In this interplay of forces, deep Earth mechanics, solar magnetism, and interstellar phenomena, we glimpse the complexity of a planet that is both a solid world and a participant in a larger cosmic ecology. Whether coincidence or correlation, the events of September 2025 offer a moment to observe the Earth not as a closed system, but as a responsive entity embedded in a changing solar environment, a reminder of our planet's fragility and its connection to forces far beyond human scale. By mid-September 2025, the Kamchatka Peninsula had become a living seismograph, its landscape trembling with a frequency that drew the attention of researchers across the globe. More than 40 aftershocks above magnitude 6 rippled through the region. In just a few weeks, each one a reminder that a major megathrust event rarely ends with a single rupture. Instead, it resets the geological clock, redistributes stress across vast tectonic distances, and initiates a cascade of adjustments that can continue for months or even years. To understand why this clustering mattered, one must return to the physics of the July 29th megathrust earthquake. When the Pacific plate slipped beneath the Yakutsk plate along nearly 600 kilometers of fault, the rupture did not simply relieve stress, it reconfigured it. Coulomb stress modelling from the United States Geological Survey demonstrated how the main shock increased failure probability on dozens of adjacent fault segments. Some regions experienced heightened compression. Others entered what seismologists call stress shadows, temporary zones, where earthquake likelihood decreases. This redistribution forms a complex tapestry of mechanical consequences, a chain of invisible tensions threading through the crust. The September 18th magnitude 7.8 quake fit the statistical signature of a classic aftershock. Its magnitude, location, and rupture plane aligned with patterns observed after historic megathrust earthquakes in Japan, Chile, and Sumatra. The event should have been unsurprising, yet scientists remained uneasy for reasons that extended beyond tectonics alone. The unease centered on timing. The September 18th quake arrived just 3 days after Earth absorbed a strong geomagnetic storm. The atmosphere shimmered with auroral activity. The magnetosphere oscillated with fluctuations measured across continents. The storm, driven by a coronal hole high-speed stream, created a prolonged period of magnetic disturbance. Unlike the sharp, instantaneous impact of a coronal mass ejection, coronal hole streams impose a slow, sustained electromagnetic pressure, an invisible wind compressing Earth's magnetic shield over many hours. This pressure induces electrical currents, telluric currents in the ground. These currents, though typically small, move preferentially through conductive structures, mineral belts, sedimentary basins, and crucially fault zones. The possibility that such currents could modulate fluid pressures or alter stress distribution along critically loaded faults has inspired decades of alternative hypotheses, yet the evidence remains elusive, the mechanisms speculative, and the mainstream scientific consensus cautious. Still, the alignment of two very different disturbances, one geological, one electromagnetic, invited renewed curiosity. Could the electromagnetic environment nudge a fault already on the edge of failure? Could a geomagnetic storm advance an earthquake by hours or days? These questions remain unresolved, but they reflect a broader truth. Earth is more than a solid body of rock. It is an electrically active system embedded in an electrically active solar environment. The September storm was not an isolated event, but part of a larger heliophysical pattern. Solar cycle 25 was rising toward its peak, and coronal holes like CH1316 had become recurring features on the solar surface, sending streams of high-speed particles toward Earth with rhythmic consistency. During September, CH1316 produced several bouts of elevated geomagnetic activity, each one adding a layer of complexity to Earth's space weather environment. Solar wind conditions during the mid-September storm were unusual. Particle density dropped to less than a proton per cubic centimetre, while velocities reached nearly 700 kilometers. Some researchers refer to this combination as a solar wind vacuum, a low-density regime that alters the balance of forces acting on Earth's magnetosphere. Whether such conditions can influence tectonic processes is unknown, but the theorized mechanisms, changes in ionospheric pressure-induced currents, modifying pore fluid distribution, electromagnetic modulation of fault friction, remain subjects of active investigation. The scientific challenge lies in scale. Earthquakes release vast amounts of energy far exceeding anything produced by changes in geomagnetic activity. Yet triggering does not require energy equivalence. Faults nearing failure can be sensitive to stress perturbations measured in kilopascals, equivalent to the pressure of holding a sheet of paper against a wall. Even subtle external influences, if timed precisely, could alter the moment of rupture. Kamchatka was primed for such sensitivity. The crust in the region had been adjusting continuously since late July, with seismicity reflecting a system near its thresholds. In this context, the September 18th quake was less a surprise than a continuation of a process already in motion. But the curious alignment with space weather conditions remains difficult to fold neatly into standard models. It is here that the broader cosmic landscape enters the narrative. As the Sun accelerated into a more active phase, an interstellar visitor, 3E Atlas, was moving through the heliosphere. Its enormous coma, already hundreds of thousands of kilometers across, interacted with the solar wind in ways unlike any local comet. Plasma structures of such size do not alter space weather conditions at Earth, but their presence illustrates the complexity of the heliospheric environment during this period. Earth, the Sun, and an interstellar comet formed a dynamic system connected through plasma magnetism and gravity. In moments like these, science meets humility. Not all correlations reveal causation. Not all patterns signify underlying connections, and yet dismissing complexity too quickly risks overlooking subtle interactions that may shape the Earth in ways we have not yet learned to measure. As the aftershocks continued through September, Kamchatka remained restless, a region adjusting to deep changes within the crust. Meanwhile, above the trembling Earth, the Sun continued to reshape its magnetic fields, and an interstellar visitor carried its ancient materials toward perihelion. In this convergence of geophysics and heliophysics, one truth endures: Earth does not exist in isolation. It responds to forces near and far, mechanical and electromagnetic, familiar and unknown. And in that delicate dance of stress and starlight, we are reminded of our place within a broader cosmic ecology, fragile, curious, and always learning. To understand the more unusual theories surrounding the September sequence, one must shift perspective from the solidity of tectonic plates to the fluid electromagnetic environment that envelops our planet. At any given moment, Earth is immersed in a continuous river of charged particles known as the solar wind, a stream so persistent that it has shaped the magnetospheres of planets, carved comet tails, millions of kilometers long, and defined the very boundaries of the heliosphere. Under ordinary conditions, this stream flows past Earth at roughly 400 km/s, maintaining a relatively stable relationship with our magnetosphere. But during periods of heightened solar activity, coronal holes, openings in the Sun's magnetic field, can accelerate these particles to extreme velocities exceeding 700 km. When such a high-speed stream collides with Earth's magnetic field, the result is a prolonged and turbulent interaction rather than the sharp impulse characteristic of a solar eruption. It was precisely this type of disturbance that Earth experienced in mid-September 2025. Solar wind density dropped to exceptionally low levels below 1 proton per cubic centimetre, creating a solar wind vacuum, a condition significantly more rare and extreme than the storm categories commonly described in space weather forecasts. In this vacuum regime, Earth's magnetosphere expands outward, no longer compressed by the typical density of solar wind particles. This expansion alters the distribution of electric currents in the magnetosphere-ionosphere system, generating fluctuations that propagate downward into the crust. These currents, known as geomagnetically induced currents or GICs, are well-documented phenomena. Utility companies monitor them because they can cause transformer heating, pipeline corrosion, and communication disruptions. Their paths follow geological structures of high conductivity, such as sedimentary basins and fault zones. Along these pathways, even small electromagnetic perturbations can produce measurable electrical flows. The controversial hypothesis suggests that under specific circumstances, such currents might influence faults already nearing failure. Unlike tectonic forces, which require immense energy to deform rock, triggering requires only a slight push, a marginal reduction in friction, a localized increase in pore pressure, or an imperceptible shift in stress orientation. In principle, electrical currents moving through fluid-filled cracks could alter electrochemical conditions affecting the stability of minerals or the viscosity of fluids trapped within fault zones. Laboratory experiments offer partial support. In controlled settings, rocks subjected to electrical currents exhibit changes in fracture propagation behavior. Fault materials respond to electromagnetic fields with modified slip tendencies. These findings do not scale cleanly to natural environments, but they demonstrate that the boundary between mechanical and electromagnetic processes may not be as rigid as once assumed. Critics point out correctly that the energies involved in GICs are orders of magnitude smaller than those associated with tectonic stress accumulation. A magnitude 7 earthquake releases roughly the energy of 32 nuclear devices, while geomagnetic variations produce currents measured in hundreds or thousands of amperes, large for electrical infrastructure but minuscule relative to forces stored in geological plates. Yet triggering does not require matching energies. It requires only the smallest internal perturbation to tip an already unstable system. The events of September 2025 presented a natural experiment. Kamchatka was in an elevated state of seismic tension following the July megathrust rupture. The aftershock sequence displayed a classic decay pattern, yet included multiple large event signs of a region adjusting to profound crustal reorganizations. Simultaneously, Earth was exposed to an unusually prolonged and intense series of geomagnetic disturbances driven by a persistent coronal hole. While mainstream models treat the two domains, geophysics and heliophysics, as separate, the timing encouraged some researchers to consider whether subtle coupling might be at play. Not because space weather causes earthquakes, but because it might influence their timing when all other conditions are aligned. Adding to this scientific backdrop was the presence of a rare celestial contributor, 3I Attilas, the interstellar object carrying a coma nearly half the diameter of the Sun. Its massive plasma envelope interacted with the solar wind across hundreds of thousands of kilometers, behaving as a natural probe of heliospheric conditions. Although its effects could not reach Earth directly, its presence underscored the complexity of the space environment. During this period, a reminder that the heliosphere is a dynamic interconnected system where solar wind magnetic fields and plasma structures converge. The solar wind vacuum thus becomes more than a technical term. It becomes a metaphor for a broader uncertainty. It marks a space where familiar models weaken, where traditional boundaries blur, and where subtle interactions may operate below our current capacity to measure. Whether these interactions influenced the September earthquakes remains an open question, one requiring caution, data, and humility. For now, the lesson is simple. Earth does not exist in isolation. Its crust, its magnetic field, and its place in the solar wind are expressions of a single interconnected system, one that responds to forces both deep beneath its surface and far beyond its sky. On September 13, 2025, Mercury slipped into superior conjunction, aligning almost perfectly behind the Sun from Earth's perspective. In celestial mechanics, this configuration occurs routinely, yet it represents a moment of geometric clarity, a straight line through space connecting three worlds. Less than 24 hours later, a G3 geomagnetic storm swept over Earth, igniting auroras far south of their usual domains and disturbing radio bands used by aviation and maritime navigation. In conventional heliophysics, the two events are unrelated. The storm originated not from planetary influence, but from a high-speed solar wind stream emitted by a persistent coronal hole. Mercury, positioned nearly 96 million kilometers away on the opposite side of the Sun, contributed no gravitational or mechanical force capable of altering solar wind conditions. And yet, for a small subset of researchers who examine these subtle electrical relationships within the heliosphere, the proximity of these events raised an intriguing question. Might planetary positions, however, faintly modulate the vast electrical circuits that span the solar system? To explore this idea, one must imagine the solar system not as a collection of isolated bodies orbiting through emptiness, but as a single electromagnetic organism. The Sun continuously emits charged particles that fill the heliosphere, forming currents that wind outward in a great spiral known as the heliospheric current sheet. Planets, each with their own magnetic fields and ionospheres, interact with these currents. In this framework, planetary alignments may subtly alter the impedance of the heliospheric circuit, just as repositioning components in an electrical network changes how current flows through a device. Such ideas remain speculative, yet they offer a conceptual framework for interpreting anomalies periods when space weather behaves more energetically than predicted. The September 14th storm was expected to reach G2 intensity, but ground-based magnetometers recorded fluctuations consistent with G3 conditions, indicating a stronger than forecast electromagnetic disturbance. The difference between the two categories may seem small, but in practice the jump represents a meaningful increase in the energy delivered to Earth's magnetosphere. During G3 storms, the magnetosphere compresses dramatically under the pressure of the solar wind. Electric currents intensify in the auroral zones, heating the ionosphere and creating dense, turbulent regions that scatter radio waves. GPS accuracy decreases as ionospheric layers shift unpredictably. Airline communication routes along high-latitude flight paths experience temporary outages. These effects are well documented and understood. Less understood are the consequences beneath the surface. Geomagnetic disturbances generate geomagnetically induced currents, GICs, that flow through the conducting layers of Earth's crust. These currents seek paths of least resistance fault zones. Aquifers mineralize belts, creating transient electrical patterns that vary from region to region. Power grids have long been vulnerable to GICs. The 1989 Hydro-Quebec blackout resulted directly from transformer damage caused by a severe solar storm, but the potential effects on geological systems remain far more difficult to quantify. Some researchers propose that GICs could alter pore fluid pressures within fault zones by modifying the electrochemical environment of fractures. Others suggest that magnetic fluctuations might influence the frictional properties of fault materials. These mechanisms operate at scales far smaller than tectonic forces, Yet triggering does not require large energies, only a slight nudge applied at the right moment when a fault is already critically stressed. September 2025 offered conditions ripe for such inquiry. Kamchatka, having endured a magnitude 8.8 megathrust event only weeks earlier, remained in a state of heightened sensitivity. Stress redistribution had left numerous faults near their thresholds. The G3 storm arriving at a moment of regional seismic instability provided a natural experiment. Would large earthquakes cluster more often during periods of geomagnetic turbulence? Critically, mainstream seismology remains unconvinced. The statistical evidence supporting such correlations is inconsistent, often riddled with selection biases, and difficult to reproduce. Earthquakes are common, geomagnetic storms are common, overlaps occur frequently by chance alone. Yet the hypothesis persists not because of definitive data, but because it touches on a deeper scientific curiosity, the possibility that Earth's interior atmosphere and electromagnetic environment form a unified system more interconnected than we currently model. In this context, the behaviour of 3I Atlas becomes symbolically if not physically relevant. As the interstellar object approached perihelion, its massive plasma coma interacted with the solar wind over a region spanning hundreds of thousands of kilometres. The presence of such a large plasma body within the inner heliosphere illustrated how dynamic and complex the Sun's electrical environment had become. Though its influence could not directly reach Earth, its existence served as a reminder that the heliosphere is not a static arena, but a constantly shifting plasma medium. The September 14th storm, intensified perhaps by factors still not fully understood, coincided with a broader pattern of solar activity. Solar cycle 25 was entering its peak, characterized by a higher frequency of coronal holes, sunspots and irregularities in the heliospheric current sheet. Planetary alignments, cometry, plasma interactions and Earth's own magnetic field participated in a complex electromagnetic choreography, one with many moving parts and few definitive causal pathways. For now, the connection between planetary alignments, geomagnetic storms and earthquakes remains speculative. The scientific community demands rigorous statistical evidence before accepting any relationship. Yet speculation, when approached cautiously, can illuminate areas where further observation is needed. It reminds us that the Sun, the planets and Earth's crust may not be independent actors, but components of a single system governed by forces both mechanical and electromagnetic. In the end, the September alignment serves as a reminder of our incomplete understanding. The cosmos, vast and subtle, often resists simple explanations, and as Earth moves through the shifting currents of the solar wind, its surface and interior respond in ways we are only beginning to measure. In the study of earthquakes, geography often appears straightforward: faults, rupture where faults exist, stresses accumulate, where tectonic plates collide and seismic waves radiate outward in predictable patterns. Yet beneath this seeming simplicity lies a planet-wide system of energy, transfer one that does not always obey the boundaries we draw on maps. Nowhere is this more evident than in the long, debated idea of antipodal effects, the hypothesis that major earthquakes can influence seismic behaviour at the point on Earth directly opposite the rupture. For most locations on the planet, an antipode falls somewhere in an empty stretch of ocean. But the antipode of the Kamchatka Peninsula, with its massive July 29th magnitude 8 earthquake, lies astonishingly close to the Drake Passage, one of the most tectonically intricate regions of the Southern Ocean. This coincidence alone is not evidence of a causal relationship, yet it has prompted renewed curiosity among researchers who study the global redistribution of seismic energy. The physical foundation of antipodal hypotheses is not without precedent. Large earthquakes generate seismic waves that propagate around the entire globe, converging at antipodal points with surprising clarity. Long-period surface waves, particularly Rayleigh and Love waves, can circle the Earth multiple times, gradually losing strength, but not disappearing entirely. Sensitive seismometers often detect these waves 12 or even 24 hours after the initial rupture. Yet the more controversial claim suggests something deeper, that these waves may not merely pass through antipodal regions, but deposit stress anomalies large enough to influence future seismic events. In this view, the Earth behaves not as a series of isolated tectonic blocks, but as a coupled system capable of transmitting stress and energy across vast distances. Most seismologists remain skeptical, pointing to the immense energy losses that occur as waves radiate outward. The fraction of energy arriving at antipodal distances is minuscule compared to that stored in local faults. The Earth's crust, they argue, is too heterogeneous, too fractured, too thick to allow meaningful stress transfer across 12 feet down 700 kilometers. The mechanical coupling required would be extraordinary, and yet the counterexamples linger. The 2004 Sumatra Andaman earthquake, one of the largest in recorded history, was followed 4 months later by a magnitude 8.6 event on the same fault system, but notably accompanied by increased activity in several antipodal regions. The 2011 Tohoku earthquake in Japan likewise showed temporal associations with unusual patterns of seismicity on opposite sides of the globe. These patterns remain statistically ambiguous, but they persist strongly enough to encourage continuing investigation. The Drake Passage, sitting at the junction of the Antarctic, South American and Scotia plates, is a region of high seismic sensitivity. Its combination of transform faults, active spreading centres and microplate boundaries creates a delicate equilibrium. When seismic waves from a massive event like the Kamchatka megathrust pass through this region, the theoretical possibility exists, however small, that they could nudge already unstable structures. Even more speculative are models involving electromagnetic antipodal effects. According to these large earthquakes, generate electromagnetic disturbances through piezoelectric and electrokinetic processes within the crust. These disturbances propagate through the planet's conductive mantle and core, potentially influencing electrical conditions at antipodal points. Such electromagnetic perturbations would travel far faster than seismic waves reaching the opposite side of the world in minutes. The evidence is sparse, but the idea underscores a broader theme. The Earth is not simply a mechanical body, but an electromagnetic one. The timing window intensifies the intrigue. Historical analyses of potential antipodal pairs often show delays ranging from 2 to 6 months between a primary event and a hypothesized antipodal response. The July 29th megathrust places the global system squarely within this proposed window as the calendar turns through October and November 2025. Whether this window holds real predictive value or simply reflects pattern seeking in noise remains disputed. Yet science progresses by examining anomalies, not ignoring them. If antipodal triggering exists, it would signify a form of global stress balancing where large ruptures must eventually be compensated elsewhere in the system. Earthquakes under this framework become not isolated events, but planetary scale adjustments in a constantly evolving equilibrium. The Kamchatka rupture released enormous mechanical energy, altering global stress fields in subtle ways that remain difficult to measure. The Drake Passage, with its tectonic complexity, represents one of several regions where these perturbations might manifest. Still, caution remains crucial. Earthquakes occur daily along the Drake Passage due to its natural tectonic activity. Identifying an antipodal response requires far more than temporal alignment. It requires changes in seismic patterns that statistically exceed background levels, pattern shifts that can be measured, not merely felt. As researchers monitor seismic networks across the globe, interest in antipodal regions has grown not because the theory has been validated, but because the current moment represents an extraordinary natural experiment. Multiple domains of potential influence converge simultaneously: residual stress from a record-breaking megathrust elevated solar activity, unusual geomagnetic conditions, and the approach of a massive interstellar comet. Each domain alone offers limited insight. Together they form a scientific landscape rich with questions. Perhaps antipodal triggering is real. Perhaps it is illusory. Yet even in raising the question, we are reminded of something essential. Earth is a dynamic, interconnected system. Its tectonic plates, magnetic fields, oceans, and deep interior do not operate in isolation. They respond to forces that travel across, through, and around the planet, some familiar, some invisible, some perhaps not yet understood. In this sense, the antipodal hypothesis serves less as a prediction than as an invitation, a reminder to view Earth not as a static sphere, but as a global organism, a system of stresses, waves, and electromagnetic pulses responding to an ever-changing cosmic environment. In the long history of astronomy, moments arise when a single discovery expands the boundaries of what scientists consider possible. The arrival of 3I Atlas, the third confirmed interstellar visitor to enter our solar system, represents such a moment. It is neither a typical comet nor a familiar asteroid. Instead, it is a fragment of another star system, an emissary that carries within it the chemistry, physics, and mysteries of a world we have never seen. The story began quietly when the Asteroid Terrestrial Impact Last Alert System Atlas detected what appeared to be a faint, unremarkable point of light. But orbital calculations quickly exposed its extraordinary nature. The object followed a hyperbolic trajectory, a path that could only result from an origin outside the gravitational control of our Sun. Where ordinary comets are bound by long elliptical orbits, 3 Atlas came in on a one-way path moving too fast to remain. What made it remarkable was not merely its origin, but its behaviour. Most comets awaken, if at all, only when they cross within 2 or 3 astronomical units of the Sun, where solar heating becomes strong enough to vaporise water ice. Yet 3I Atlas was active far earlier, displaying a glowing coma at distances where temperatures should keep most ices locked in place. That early activity suggested a composition rich in highly volatile materials, such as carbon dioxide and exotic ices common to the cold molecular regions between stars. Observations from the Hubble Space Telescope confirmed this suspicion. The coma surrounding the object extended roughly 700,000 kilometers in diameter, nearly half the width of the Sun. The nucleus itself was likely no more than 3-6 kilometers, across a mountain-sized fragment generating a sphere of gas large enough to fit 50 Earths side by side. This extraordinary ratio between nucleus size and coma size has few analogues in comets native to our solar system. The scale alone demanded explanation. To generate such a massive coma at such a distance, 3I Atlas must possess both highly volatile ices and a surface structure conducive to rapid sublimation. In this way, the object acts as a natural probe of interstellar chemistry. Its gases released as hydrocarbons, carbon dioxide, carbon monoxide, and more exotic compounds give astronomers rare insight into the chemical makeup of distant star-forming environments. Yet chemistry alone could not explain the coma's structure. Observers noted an unusual phenomenon forward brightening where the brightest portions of the coma appeared ahead of the object, in its direction of motion rather than trailing behind it. Ordinary comets form comas that remain largely symmetrical, with dust tails curving away from the Sun. But 3I Atlas displayed asymmetric jets patterns consistent with rapid rotation or heterogeneous patches of volatile-rich material concentrated on one hemisphere. The rotational dynamics offer clues to its origins. An interstellar object may have experienced billions of years of bombardment by cosmic rays, micrometeoroids, and collisions in its native system before being ejected into interstellar space. Over such immense time scales, surface layers erode and internal structures fracture. It is possible that large pockets of volatile ice lie close to the surface, ready to sublimate even under weak solar illumination. Yet the most fascinating aspect of 3I Atlas lies not in its physical structure, but in its implications for heliophysics. The coma's enormous scale effectively creates a massive plasma interaction zone, a region where charged particles from the solar wind collide with neutral gas molecules, generating ions that shape the object's electromagnetic environment. For scientists studying plasma physics, this interaction represents a natural laboratory far larger than any human-made experiment. The vast coma acts as a net dragging through the solar wind sampling magnetic field structures, particle populations and turbulence across hundreds of thousands of kilometers. As solar cycle 25 approached its peak, the heliosphere grew increasingly active. Coronal mass ejections, high-speed solar wind streams, and shifting magnetic fields created conditions ideal for studying plasma interactions. With 3I Atlas embedded in this environment, astronomers gained an unprecedented opportunity to observe how interstellar materials respond to the dynamic solar system. Still, the arrival of such an object during a period of heightened solar activity invited more speculative questions. Could the solar wind influence the coma's expansion in ways unseen in native comets? Could the immense coma in turn affect local solar wind properties? While such possibilities remain speculative, sophisticated models show that comets can generate bow shocks, magnetic draping effects and particle acceleration zones, phenomena often observed around planets and even stars. The scientific excitement surrounding 3I Atlas is matched by the deeper philosophical resonance it evokes. Interstellar objects are more than icy bodies. They are physical memories of their parent systems. They carry the signatures of distant suns, ancient collisions, and primordial chemistry. When they enter our solar system, they provide a glimpse into environments inaccessible to any spacecraft. The arrival of 3 Atlas then becomes a moment of cosmic significance. Not because it threatens Earth. Its closest approach remains more than 150 million kilometers away, but because it reminds us that the solar system is not isolated. Objects wander between stars. Some escape their homes, some arrive on our doorstep. Each one challenges our understanding of formation processes, interstellar chemistry, and the diversity of worlds beyond our Sun. As 3 Atlas approaches perihelion, it invites us to observe, not to fear. To measure, not to assume. To acknowledge that our solar system is part of a larger cosmic flow, a place where even brief visitors from the space between stars can reshape our scientific imagination. And perhaps as it glides through the inner solar system, it asks us to remember that the universe is a vast and open system, full of stories still unfolding, and that sometimes the greatest discoveries come not from the planets we expect, but from the travellers who arrive unannounced. To understand the scale of 3I Atlas, one must set aside ordinary intuition. Most comets, even the great ones, create comas only tens of thousands of kilometres across. Impressive, yes, but still confined, still shaped by the familiar physics of our solar system. 3I Atlas is different. It carries with it the imprint of an environment colder, darker, and chemically stranger than any region where solar comets form. The latest measurements place its coma at roughly 700,000 kilometers in diameter, more than half the width of the Sun. To envision this, imagine a sphere so large that Earth, tiny by comparison, could travel for hours inside it without reaching an edge. The nucleus, meanwhile, is no more than a few kilometers wide, a speck generating a planetary scale envelope. That ratio defies our usual sense of scale, stretching the imagination, just as it stretches our models. The mechanics behind this coma begin with sublimation, the direct transition of solid ice into vapour under the influence of solar radiation. In ordinary comets, water ice dominates, and sublimation begins within 2 or 3 astronomical units of the Sun. But 3I Atlas is rich in carbon dioxide and carbon monoxide ices that evaporate at far lower temperatures. This explains its unusually early activation. It began venting gases long before it approached the inner solar system. Yet composition alone cannot explain the sheer size of the coma. The outgassing appears not only vigorous but asymmetric, focused in regions that brighten ahead of the nucleus rather than behind it. This forward brightening suggests that the rotation of 3I Atlas exposes pockets of volatile material intermittently creating jets that push outward in complex patterns. As these jets expand, they interact with the solar wind, creating a dynamic boundary, where neutral gas becomes plasma. This boundary, where solar photons strip electrons from gas molecules, marks the transition from a passive dust cloud to an active plasma environment. Within this environment, ions follow magnetic lines rather than ballistic trajectories. The solar wind flows through the coma like a river around a boulder. Magnetic fields bend, twist and reconnect. A bow shock develops upstream, marking the region where the solar wind first encounters resistance. Downstream, the ion tail stretches millions of kilometers, pulled taut by the continuous flow of charged particles. The coma thus becomes not merely an illuminated cloud, but a laboratory of plasma physics on a scale unattainable on Earth. Particle acceleration, charge exchange, and magnetic draping, all processes studied in the atmospheres of planets, and the tails of comets occur here on a grand scale. With 3 Atlas embedded in a period of elevated solar activity, the interactions become even more pronounced. Scientists track these phenomena through a suite of space and ground-based instruments. Infrared telescopes reveal the thermal emission of dust grains. Spectrometers detect signatures of carbon dioxide, hydrocarbons, and exotic ices. Radio telescopes monitor the ionized components of the coma, mapping its electromagnetic behaviour as it responds to fluctuations in the solar wind. The James Webb Space Telescope, sensitive to faint chemical fingerprints, provides unprecedented insight into the molecular makeup of the gas. The implications reach far beyond simple cometary science. Interstellar objects preserve information about the environments in which they formed stellar nurseries, protoplanetary disks, or turbulent regions shaped by supernovae. Their chemistry is a record of cosmic processes billions of years old. When such an object interacts with the solar wind, it reveals not only its own history but the physics of the heliosphere itself. The sheer size of 3I Atlas's coma means that it samples a broad swath of solar wind conditions. Regions of varying magnetic strength, density and velocity imprint themselves on the structure of the ion tail. This makes the comet a weather vane for space weather, a drifting, naturally occurring probe capable of tracing conditions across vast distances. Some researchers speculate that the coma's enormous dimensions could influence local solar wind flow, creating feedback effects that ripple outward. While these ideas remain speculative, they hint at how little we truly understand about interactions between plasma structures of this size and the heliophysical environment. What is certain is this: as 3I Atlas approaches perihelion, its coma will continue to expand. Solar heating will intensify. New jets will erupt from volatile-rich regions. The ion tail will lengthen, brightening briefly before fading into the interplanetary medium. And through all of this, the object will remain a silent messenger from another star, its vast, luminous breath, a reminder of how small our planet is in comparison, and how much there is left to understand. In observing its passage, we find not only scientific data, but a moment of perspective, a glimpse of the immense processes shaping our cosmic neighbourhood, and a reminder that even the smallest fragments of distant worlds can reveal truths on a scale beyond comprehension. Speculation has always been a quiet companion to scientific discovery. Even the most disciplined researchers entertain questions that lie just beyond the reach of data, because throughout the history of astronomy, anomalies have often revealed new laws of nature rather than errors of observation. When Oumuamua accelerated without a visible tail, when Borisov arrived with chemistry unlike that of any known comet, when the first interstellar dust grains were isolated from meteorites, each event expanded the boundaries of what was considered possible. Within that same spirit of curiosity, a provocative question emerges around 3I Atlas, an object whose behaviour strains the conventional limits of comet physics. What if this interstellar visitor is not merely a frozen relic of another star system, but a form of engineered technology, an enormous plasma-based structure designed to harvest stellar energy as it travels between suns? The idea is speculative, yet it arises not from fantasy, but from a sequence of observations that collectively form an unusual pattern. The nucleus of 3I Atlas is small, perhaps only 3 to 6 kilometers in diameter, yet it produces a coma roughly 700,000 kilometers wide, rivaling half the diameter of the Sun. The ratio between solid core and surrounding envelope is unprecedented among known natural comets. Sublimation of volatile ices can explain vigorous outgassing, but the scale of the coma, and the fact that it continues expanding at distances where water ice remains inert, suggests a composition rich in carbon dioxide and carbon monoxide volatile ices that sublimate far earlier than water. This accounts for part of the phenomenon, yet the efficiency of the expansion is remarkable, almost engineered in its precision. If one imagines a technology designed to operate within stellar winds, plasma becomes an ideal structural medium. Charged particles respond to magnetic fields, allowing enormous surfaces to be created without physical mass. A craft built to collect energy, navigate interstellar space, or analyze magnetic fields could deploy a plasma envelope many thousands of times larger than its physical core. It would require minimal material and could be shaped dynamically, by modulating outgassing patterns or using magnetic confinement. Such a design aligns with theoretical concepts like magnetic sails, plasma tethers, and magnetohydrodynamic collectors technologies that, while beyond our engineering capability, obey known physical principles. A curious observational feature supports this speculative idea. The coma of 3I Atlas is brightest not behind the nucleus, as in typical comets, but ahead of it. This forward brightening suggests asymmetrical release of gas, or directed jets that counteract the solar wind. If controlled outgassing were being used to orient or stabilize the object, the resulting coma would appear very similar to what astronomers are currently observing. Natural explanations remain plausible: irregular surface geometry, rotational venting, or fragmentation, but the structural coherence of the coma raises questions about whether this asymmetry reflects a deeper underlying mechanism. The possibility becomes more interesting when considering what purpose such a structure might serve. An interstellar civilization seeking to explore or communicate across vast distances might rely on autonomous probes capable of sustaining themselves for millions of years. A device that harvests stellar wind energy through a plasma envelope could generate enormous electrical currents, storing them internally or using them for propulsion. Even at low efficiency, a cross-sectional area hundreds of thousands of kilometers wide intercepts immense solar wind flux. The energy harvested from a single pass near a star could potentially power a probe for centuries. Another function might be passive astrophysical surveying. A plasma envelope of this scale is an exquisite sensor array. Variations in magnetic field strength, solar wind velocity, particle density and turbulence become imprinted on the structure in real time. By analysing the way the coma stretches, brightens or rotates, a probe could map heliospheric conditions with extraordinary sensitivity. The ion tail stretching millions of kilometers downstream would register changes in the solar wind long before spacecraft near Earth detect them. Even if constructed for observation rather than communication or propulsion, such a probe could gather data on a scale unmatched by any human-built mission. Still, caution is necessary. Every observed feature of 3I Atlas has a potential natural explanation. Interstellar comets contain exotic ices whose sublimation thresholds differ from those of local comets. Their surfaces may contain materials processed in environments unlike any found in our solar system. Forward brightening can arise from rotation, fragmentation, or jets pointed toward the direction of travel. A massive coma may simply reflect volatile rich composition rather than engineering. Extraordinary claims require evidence artificial spectral lines, coherent radio emissions, non-gravitational accelerations inconsistent with known physics. None have been detected, yet the absence of evidence is not necessarily evidence of absence. A civilization capable of launching probes across interstellar distances might also prefer to avoid broadcasting their presence. Mimicking natural comet behavior could be a deliberate design choice, ensuring stealth, minimizing interference, or maintaining scientific objectivity. The most efficient interstellar probe might look indistinguishable from a fragment of rock and ice. In the end, whether 3I Atlas is purely natural or something more is less important than what its presence reveals. It demonstrates that interstellar objects traverse our solar system, regularly carrying ancient chemistry, unfamiliar physics, and the potential for insights into the formation of distant stars. Its coma, vast enough to rival the Sun's radius, acts as a natural detector of heliospheric forces, and its behaviour reminds us that our understanding of cosmic phenomena remains incomplete. Perhaps 3I Atlas is simply a remarkable comet. Perhaps it is something engineered drifting across the galaxy with quiet purpose. Either way, its passage invites us to look more closely, think more broadly, and recognise that the universe is a place where natural and artificial wonders may coexist, each waiting to be discovered. The idea that earthquakes could be influenced by forces beyond Earth's crust is one that most seismologists reject outright, not because it is impossible, but because it edges too close to the boundaries of what science can comfortably test. Yet history shows that the most unsettling truths about the universe often live in those borderlands where speculation meets data, where anomalies refuse to fit the expected pattern. The notion that certain earthquakes might be nudged into motion, not created, but triggered by changes in the electromagnetic environment, has drifted through scientific literature for decades. Most researchers dismiss it as fringe. Others quietly acknowledge that the correlations, though inconclusive, are persistent enough to warrant attention. And now, with 3I Atlas dragging a plasma envelope hundreds of thousands of kilometers wide through a magnetically turbulent solar system, the question resurfaces with uncomfortable clarity. What if some seismic events are not merely geological, but responses to directed energy? The key distinction in this hypothesis is that triggering does not require remotely injecting the energy of an earthquake. The energy for a magnitude 7 or 8 event has already accumulated slowly within the rocks, locked behind friction, until something, a sudden pressure, change of fluid shift, or a microscopic change in the electrical properties of minerals reduces the threshold enough to allow rupture. Laboratory studies have shown that electromagnetic fields can influence rock strength, alter pore pressure in water-bearing fault zones, and even accelerate the nucleation of microfractures. These effects are small, but on a fault already balanced at the edge of failure, tiny perturbations can produce massive consequences. The same principle governs avalanches and landslides. A single snowflake, a lone pebble, or a faint vibration can release the stored energy of an entire mountainside. From this perspective, the most provocative question is not whether electromagnetic forces could theoretically trigger an earthquake, but whether anything in the sky could generate the right conditions at the right moment. Solar storms already demonstrate the power of natural electromagnetic disturbances. When high-speed solar wind streams arrive, they can plunge Earth into geomagnetic storms powerful enough to disrupt GPS satellites, induce currents strong enough to damage transformers, and alter the flow of electrical charge across continents. These storms can affect pipelines, aviation systems, and low-orbit spacecraft, each a testament to how deeply Earth's systems are influenced by solar activity. If tectonic faults are as sensitive as some studies suggest, then the link between electromagnetic bursts and seismic timing cannot be dismissed outright. And here enters the most unsettling layer of the hypothesis, the possibility that an object like 3 Atlas, if artificial or partially engineered, might create electromagnetic conditions capable of interacting with planetary crusts. A structure capable of stretching a plasma envelope across hundreds of thousands of kilometers would by necessity generate or manipulate magnetic fields on a scale we barely understand. If such a craft needed to test planetary environments, map subsurface structures, or calibrate its own sensing systems, inducing small perturbations in Earth's electromagnetic layers, could produce seismic responses that would register to human instruments as ordinary earthquakes. Even a natural interstellar object could inadvertently produce electromagnetic effects unfamiliar to our models, simply because we have never studied anything quite like it, this close to the Sun. But even if one grants the theoretical possibility, the leap from theory to intention is vast. To suggest that an advanced intelligence might deliberately probe Earth's crust through seismic triggering is to wander far beyond established science. Yet history reminds us that advanced civilizations, if they exist, would likely possess tools for sensing planetary interiors as easily as we map coastlines. On Earth, scientists already use controlled vibrations, underground detonations, and electromagnetic pulses to probe geology. An extraterrestrial analogue might scale these methods to planetary magnitude, perhaps using plasma-based systems rather than chemical explosives. If such a probe were surveying Earth, the resulting signals would appear to us not as technological signatures, but as natural earthquakes occurring at statistically unusual moments. Still, extraordinary claims demand extraordinary evidence, and for now the evidence remains ambiguous. Earthquakes continue to follow the patterns expected of tectonic systems, even if their timing sometimes coincides suspiciously with solar disturbances. 3 Atlas shows no definitive markers of artificiality, and the Earth, resilient and restless, has produced countless quakes long before interstellar objects entered our awareness. The danger lies not in considering the hypothesis, but in leaping to conclusions unsupported by data. The value of such speculation is not certainty but perspective. It forces us to reconsider the quiet interactions between space and planet, between magnetic storms and seismic rhythms, between what we assume is natural and what might be part of a larger cosmic system we barely perceive. In the end, the directed energy hypothesis invites humility more than fear. Whether earthquakes are influenced by cosmic conditions or remain strictly geological, the universe has shown us again and again that its mechanisms are stranger, subtler, and more interconnected than we imagine. And as 3 Atlas moves deeper into the Sun's magnetic domain, the opportunity to observe these interactions, natural or otherwise, has never been greater. October 2025 unfolds like a convergence engineered by forces far beyond human intention. A moment when multiple cosmic systems seem to inhale and exhale in synchrony, creating patterns that both invite study and resist explanation. At the centre of this alignment is the new moon of October 21st, an ordinary astronomical event that becomes extraordinary only because of the company it keeps. The moon slips into its invisible phase just as Earth traverses heightened geomagnetic turbulence, just as cometary visitors brighten in the night sky, just as 3i Atlas approaches a region of the Sun where its massive plasma envelope will be reshaped by an increasingly violent magnetic environment. None of these events taken individually are unprecedented, yet their simultaneous occurrence creates a sense of resonance that scientists try to ignore, mystics try to interpret, and observers cannot help but feel. In this sense, October becomes a kind of cosmic crosspoint, a place where natural cycles intersect in ways that expose the delicate electrical scaffolding that binds Earth to its star. This convergence demands more than curiosity. It demands discipline, because moments that feel symbolic can also mislead. The new moon, for instance, carries no known physical influence over geomagnetic storms or seismic systems. Its gravitational pull is real but predictable, shaping tides and subtly modulating stress across the crust. Yet this particular new moon arrives as the Sun's magnetic field enters a highly dynamic configuration, its corona threaded with open field regions that release high-speed solar wind streams directly toward Earth. These streams, sometimes exceeding 700 km per second, stretch Earth's magnetosphere, induce electrical currents along the surface, and create auroras that flicker across continents unaccustomed to such displays. It is a scientifically predictable spectacle, yet one that feels mythic when observed in concert with the deep quakes of the Pacific Rim or the silent arrival of interstellar dust. What complicates the picture is that multiple comets Swan Lemon, Shomas Christensen, and of course the enigmatic 3i Atlas are all interacting with the solar wind at the same time, creating vast plasma structures that drift across heliospheric currents like luminous sails. This swarm of objects, each developing ion tails that trace the invisible geometry of the interplanetary magnetic field, effectively becomes a distributed sensing network. They reveal through their shapes and motions where the solar wind compresses, where the magnetic field kinks, where turbulence forms. To the trained eye, they are diagnostic tools as much as astronomical wonders. Yet even as they illuminate heliospheric processes, they raise unsettling questions about feedback. If cometary plasma can be shaped by solar conditions, can it also shape them? Most models say no. A few fringe studies say maybe. And the truth still beyond our instruments remains suspended somewhere between those poles. Meanwhile, Earth continues its own dance of volatility. The lingering aftershock sequence in Kamchatka, the anomalous clustering in the Southern Ocean, the shallow tremors along the Basin Range province. Each event is individually explainable, yet collectively they create a global seismic tapestry that feels unusually dense. The timing may be coincidence, but it joins the broader pattern of October's unrest solar storms, comet activity, interstellar plasma, and tectonic release, all operating in overlapping frequencies. It is here that scientific skepticism must coexist with scientific openness. The established view holds that Earth's crust is governed by the slow dynamics of plate motion, and that electromagnetic variations cannot meaningfully alter fault stability at large scales. The alternative view, occupying the edges of geophysics, suggests that subtle changes in ionospheric charge, global electric circuits, or magnetospheric compression could nudge critically loaded faults toward rupture. This view remains unproven, yet October tests it in ways that no dataset has tested before, simply because the convergence is so rare. As 3i Atlas approaches perihelion on October 30th, the object's coma may grow to exceed 1 million kilometers in diameter. Within that vast envelope, ionization and magnetic draping will produce complex electrical phenomena, currents, charge separation, and plasma instabilities that human instruments will barely be able to track. Astronomers know what natural comets do near perihelion, but an interstellar object is another category entirely carrying ices and dust that formed under unknown stellar conditions. When these materials interact with the Sun's magnetic layers, they may produce spectral lines emissions or field disturbances that challenge existing cometary theory. For scientists, this encounter is a once-in-a-lifetime laboratory in motion. For those attuned to patterns, it feels like a chapter in a story whose implications stretch beyond astrophysics. The unknown danger of October is not catastrophic impact or extinction level threat. Those fears belong to fiction, not science. The real uncertainty lies in interpretation. If Earth experiences major seismic events during this window, the correlations will energize hypotheses that many researchers dismiss. If Earth remains quiet, those same hypotheses may lose their footing. Either outcome provides clarity, but only if we observe and interpret the data without surrendering to fear mythology or premature conclusions. The universe is not signaling doom. It is simply behaving according to its own vast electromagnetic rhythms that humanity is only beginning to perceive at planetary scale. And in that sense, October 2025 becomes not an omen, but an invitation to study, to question, to understand a little more of the cosmic ocean through which Earth drifts. The final months of 2025 present a spectacle that feels less like a sequence of isolated astronomical events, and more like a coordinated performance stitched together by the quiet logic of cosmic physics. Astronomers call it a comet swarm, a term that sounds sensational until you realise it is merely a factual description. 7 luminous objects, each following its own ancient trajectory, now converging on the inner solar system simultaneously. Their combined presence transforms the space around the Sun into a layered experiment in plasma dynamics, magnetic topology, and interstellar chemistry. 3i Atlas remains the headliner, a visitor from deep space dragging behind it a carbon dioxide-rich coma that spans nearly half the Sun's diameter, but it does not drift alone. Comets. Swan Lemon Christensen. Shomas and several others form a distributed constellation of icy laboratories, each shaped by solar radiation, each sculpted by high-speed solar wind streams, each responding differently to the chaotic electromagnetic environment of solar cycle 25. To understand why scientists regard this swarm as unprecedented, one must imagine the inner solar system as a vast fluid, one filled with charged particles, magnetic fields and waves of turbulence that ripple outward from the Sun. Every comet, no matter how small, interacts with this fluid. Neutral gas escaping from its nucleus becomes ionized by sunlight, then swept into long, glowing ion tails that trace the structure of the interplanetary magnetic field. Dust particles pushed by a radiation pressure arc away in gentle curves that reveal the past motions of the object and the density gradients of surrounding plasma. When multiple comets pass through this environment simultaneously, their tails function like ink dropped into water, revealing hidden currents, sheer flows and eddies that are normally invisible. To solar physicists, this swarm is not merely beautiful, it is diagnostic. It provides the kind of multi-spatial sampling of heliospheric conditions that human spacecraft cannot achieve, offering measurements across millions of kilometers in real time. Comet Swan, perhaps the most photogenic of the group, unfurls a tail that spans several degrees of sky 5 times the width of the full moon. Its dust plume, illuminated by the low-angle sunlight of October, acts as a natural scattering experiment, revealing gradients in particle density along the solar wind's flow. Comet Lemon D, brightening faster than predicted, has become a puzzle of its own. Its photometric curves suggest an outburst or structural fragmentation, a reminder that comets evolve rapidly when subjected to thermal stress and magnetic compression. Christensen, a periodic comet with a well-documented orbit, serves as a kind of control sample, allowing researchers to compare the predictable behaviour of a solar system native against the strange dynamism of 3i Atlas. Meanwhile, Shomas offers a slower, steadier development, its coma thickening at a rate that aligns with classic sublimation models, providing yet another baseline for comparison. The mechanics behind comet tail formation become particularly fascinating in the context of this swarm. Dust tails respond to photons' tiny packets of light momentum that push particulate matter into vast arcs. Ion tails respond to magnetic fields snapping into alignment with solar wind lines like glowing streamers in an invisible cosmic storm. During periods of heightened solar activity, coronal mass ejections can collide with these ion tails, compressing them, folding them, or severing them entirely in what astronomers call disconnection events. Missions such as ESA's Solar Orbiter and NASA's Parker Solar Probe have documented these events, but never in a context with so many comets simultaneously available to witness the phenomenon. Each disconnection reveals where the magnetic field reverses polarity, or where solar wind density spikes moments that offer clues to the Sun's internal magnetic architecture. This swarm arrives at an especially turbulent moment in solar cycle 25. Sunspot activity is higher than many forecasts anticipated, and high-speed streams from coronal holes have repeatedly slammed into Earth's magnetosphere, creating geomagnetic disturbances that ripple through satellites' power grids and the upper atmosphere. When these disturbances meet cometary comas, the results are even more complex. The plasma envelopes of comets become temporary laboratories for studying shock formation charge exchange processes and the microphysics of ionized gas interacting with variable magnetic fields. For 3 Atlas, whose coma is hundreds of thousands of kilometers wide, the interaction becomes extraordinary. Its ion tail is expected to stretch millions of kilometers downstream, a faint electric ribbon responding to the full force of the solar wind. For a brief moment in cosmic history, the heliosphere is being probed by multiple natural instruments all at once. The scientific value of this configuration cannot be overstated. For decades, heliophysicists have struggled to measure the Sun's magnetic field on scales larger than the orbits of the inner planets. Spacecraft provide point measurements precise but limited in scope. Comets provide distributed measurements simultaneously sampling conditions across different latitudes, longitudes, and heliocentric distances. When tracked carefully, the evolution of their tails allows researchers to reverse engineer magnetic gradients, turbulence levels, and shock geometries that no spacecraft fleet could match. In effect, the swarm transforms the inner solar system into a temporary observatory. The Sun writes its magnetic patterns into ionized gas, and comets reveal the script. But the swarm also raises philosophical questions about the nature of cosmic timing. Is this convergence merely a statistical oddity, a rare alignment produced by chance? Or does it hint at deeper cycles in cometary dynamics, solar behavior, or the gravitational architecture of the Milky Way scientists by necessity lean toward the former? Patterns must be testable before they can be trusted. Yet the recurrence of comet clusters in historical records from ancient Chinese chronicles to the observations of medieval astronomers suggests that these alignments may be more common than previously assumed. It is only now, with modern instruments and global dissemination of data, that humanity can appreciate the full choreography unfolding around our star. Above all, the comet swarm of 2025 reminds us that the solar system is not static. It is a dynamically charged theatre where objects of ice and dust become luminous instruments, where the Sun's moods ripple outward for billions of kilometers, and where interstellar visitors occasionally drift in, brushing against the magnetic skin of our star before vanishing again into the dark. As these 7 comets pass through the inner solar system, each shedding ancient material, each tracing invisible currents, each revealing a different facet of solar behavior, they offer a fleeting, humbling glimpse into the living plasma ocean that surrounds us. And for that brief window, Earth becomes an audience to a rare cosmic symphony, one whose echoes may shape heliophysical research for decades to come. Solar Cycle 25 has unfolded like a slow and rising tide of electromagnetic force, a kind of invisible weather that few humans notice but every spacecraft can feel. To describe it as a storm is not quite accurate. A storm is temporary, chaotic, and fleeting, but what surrounds Earth now is more like a sustained pressure, a continuous reshaping of the electromagnetic architecture that protects our world from the Sun. Scientists call it an active maximum, a period in the Sun's 11-year rhythm when magnetic fields twist into knots, snap open in violent flares, and release billion-ton clouds of charged particles outward into the heliosphere. Yet the poetic truth is simpler. The star that nurtures our existence has awakened, and with that awakening comes an energy tsunami sweeping silently through space. Unlike the curved spirals of hurricanes or the towering walls of terrestrial cyclones, this tsunami carries no air, no water, no sound. It is pure interaction, electric, magnetic, atomic, magnetic, and we sit inside it as unsuspecting swimmers carried by currents we can neither see nor escape. The numbers themselves feel almost surreal. During the past year, sunspot counts have exceeded original projections, with clusters forming the size of continents, their magnetic loops rising and falling like scorching mountains. Solar flares have erupted with intensities equivalent to billions of nuclear detonations, releasing radiation that travels to Earth in under 8 minutes. Coronal mass ejections, vast luminous exhalations of the Sun, have swept across the inner solar system with velocities exceeding 1/600 km per second. These events do not strike Earth directly in the physical sense, but they slam into its magnetic field, compressing it, rattling it, making it ring like a struck bell. What makes this moment in history so scientifically unprecedented is not merely the solar activity itself, but the infrastructure humanity has constructed to observe it. For the first time in any solar maximum, our instruments occupy nearly every region of near-solar space. Parker Solar Probe dives through the Sun's outer atmosphere, measuring magnetic reconnection, events, at distances no previous mission dared approach. Solar Orbiter maps the polar regions of the Sun where the magnetic cycle originates. Cluster satellites, ground magnetometers, deep space monitors, and imaging telescopes all synchronize their observations, producing a multi-layered portrait of solar behavior that has never existed before. We are in a quiet and unassuming way witnessing the Sun with more clarity than any civilization in human history. This clarity arrives at a moment when the inner solar system is unusually populated with plasma-bearing objects. The comet swarm, dominated by the colossal coma of 3I Atlas, drifts through the same solar wind that carries the Sun's electromagnetic turbulence. Each comet is a sensor, an antenna of gas and ionized dust. Their comas swell, ripple and deform with every incoming shockwave. When a coronal mass ejection sweeps past, it sculpts the ion tail like a windstorm shaping a sand dune. When a magnetic field reversal passes through the tail, can disconnect entirely a ghostly ribbon torn from its source. In this way, comets inadvertently reveal the structure of the heliosphere. The Sun writes turbulence into space, and comets make it visible. This is why some researchers have begun calling the current conditions a distributed heliophysical observatory. 3 Samdawa Atlas, with its coma, hundreds of thousands of kilometers wide, functions like a massive plasma probe, absorbing solar particles, ionizing them, and re-radiating their energy as faint emissions detectable by X-ray and ultraviolet instruments. Comet Swan acts like a solar wind vane, its tail lengthening when particle density increases and thinning during periods of decreased solar output. Even smaller bodies in the swarm like Christensen and Lemon provide localized measurements of magnetic field strength and solar wind velocity. It is unusual enough for one bright comet to pass through the inner solar system during a solar maximum. 7 passing simultaneously under heightened electromagnetic conditions is nothing short of extraordinary. Earth, suspended within this dynamic environment, becomes a participant in the same invisible drama. Geomagnetic storms ripple through its magnetosphere, causing auroras to reach latitudes where they are rarely seen. Small oscillations in magnetic field strength induce currents in power grids, pipelines, and even the human nervous system. Airline routes shift to avoid radio blackouts. GPS satellites correct for ionospheric distortion. Radio operators detect static that speaks in the strange mathematical rhythms of cosmic interference. Humans often forget that Earth is not shielded by a dome, it floats inside an electromagnetic sea, and solar maximum turns that sea into a restless shimmering tide. Yet there is another dimension to this energy tsunami that rarely enters scientific discussion, but permeates cultural records across centuries. Human societies tend to become restless during intense solar periods. Historical correlations hint at increased creativity, increased conflict, and increased sensitivity to cosmic symbolism during solar maxima. Whether this arises from electromagnetic influence, psychological projection, or coincidence is still a point of debate. But what is clear is that during times like this, humanity notices the sky, interprets it more intensely, and projects meaning onto cosmic patterns in ways that reflect collective consciousness. In 2025, this tendency is sharpened by the simultaneous comet swarm, by the deep space nature of 3I Atlas, and by the magnified electromagnetic presence of the Sun. When all these elements converge, solar, maximum distributed comet probes, interstellar chemistry, fluctuating geomagnetic conditions, they form something more than a scientific event. They form a moment of cosmic visibility, a reminder that Earth is not drifting alone. It is embedded in a system of forces that shape continents, influence atmospheres, and ripple through planetary magnetic fields. For now, the energy tsunami remains primarily an opportunity, a chance to observe the Sun's behaviour at peak intensity, while simultaneously studying how multiple comets respond to the same environment. The data collected in these months will influence heliophysics for decades. It will refine space weather forecasting, deepen our understanding of plasma physics, and reveal intricacies in the solar cycle that have remained hidden for generations. As scientists watch the solar wind pulse against the cometary swarm, as satellites record magnetic storms rippling through Earth's magnetosphere, a quiet recognition spreads through the scientific community. This is one of those epochs where the universe reveals itself not in fragments or isolated anomalies, but in sweeping systems. The sun, the comets, the solar wind, the magnetosphere, each part becomes visible through the interplay of all the others. In this sense, the energy tsunami is not a threat, but an illumination, a temporary unveiling of forces that usually remain cloaked in invisibility, and so the world watches measuring particles and magnetic fields, tracking the plasma tails of wandering comets, listening to the electric heartbeat of the sun. A season of cosmic clarity, rare, delicate, and scientifically priceless, has arrived. And when it passes, humanity will understand both the sun and the space that surrounds it just a little more deeply than before. The closer we move toward the end of this extraordinary year, the more apparent it becomes that cosmic events rarely occur in isolation. They ripple, overlap, interfere, and amplify one another, like waves moving across the same vast ocean. What we witnessed in late 2025 was not a single anomaly, nor even a chain of them, but a convergence, an intricate symphony of solar activity, interstellar chemistry, seismic restlessness, and human perception braided into the same moment of time. And perhaps most revealing of all is the growing recognition that our interpretations of these events are shaped as much by our internal states as by the physics unfolding around us. When the sun brightens, when comets ignite, when fault lines strain in silence, humanity responds not only with measurement and analysis, but with meaning. We look outward to understand what is happening inward, and the cosmos, indifferent yet generous, provides symbols large enough to hold our questions. In scientific terms, the period surrounding October and November 2025 represents an unparalleled opportunity to study multi-domain interactions across the solar system. Advanced instrumentation on Earth and in orbit captured every nuance of solar plasma, each shift in solar wind velocity, every oscillation in Earth's magnetic field. The interstellar visitor 3I Atlas, with its enormous carbon dioxide-rich coma, acted like a floating detector array, absorbing scattering and reshaping charged particles across a sphere nearly as wide as half the Sun. Meanwhile, seismic networks continued to record aftershocks in Kamchatka and beyond, printing out minute by minute the stress signatures of a planet adjusting itself after massive geological release. Yet beneath the graphs and readings, something subtler was being measured, the collective breath of a species watching the heavens, with a mixture of awe, anxiety, and awakening. Psychologists and neuroscientists have long noted that human cognition is not immune to environmental patterns. During solar maximum fluctuations in geomagnetic conditions have been linked tentatively, controversially, to changes in sleep cycles, mood variants, even decision-making patterns. Studies remain inconclusive, but the hypothesis persists that humanity, despite its technological insulation, still carries ancient biological sensitivities to the electromagnetic environment it evolved within. During periods of heightened solar activity, these subtle influences may deepen, acting on the edges of consciousness rather than the centre. This does not diminish human agency. Instead, it suggests that the cosmos may play a silent supporting role in how we move through collective moments of tension or transformation. And 2025, with its unprecedented cosmic alignments, provided fertile ground for such speculation. One of the most intriguing questions raised during this period concerns the nature of coincidence itself. When multiple dramatic events occur close together, earthquakes, geomagnetic storms, political upheavals, astronomical anomalies, our pattern-oriented brains begin stitching them together seeking coherence where there may be none. Statistically, coincidences grow more common as the total volume of global data increases, yet human experience is not statistical, it is narrative. We live through events linearly, emotionally, intuitively. When the Earth shakes days after a geomagnetic storm, when a luminous interstellar comet approaches the Sun at the same moment that social systems falter. Part of us leans into the possibility that these events are related not because science confirms it, but because the symbolism resonates. The universe feels communicative, as though the movements of plasma and stone are part of a larger pattern we are meant to witness even if not fully comprehend. At the same time, the scientific method demands clarity. Correlation is not causation, and cosmic symbolism is not data. Researchers examining potential links between solar activity and seismic events find mixed results, with most mainstream analyses concluding that any direct causal mechanism remains unproven. Electromagnetically induced currents in Earth's crust are real and measurable, but their magnitudes appear too small to trigger large earthquakes on stable fault systems. Instead, these currents may play a role only when a fault is already critically loaded, an idea that keeps the door open but far from settled. The possibility remains suspended in that space between what is known and what is plausible, a region familiar to every frontier of science. What makes the 2025 convergence especially fascinating is that it exposed with rare clarity how much we do not understand, not only about comets or solar cycles or geomagnetic disturbances, but about the full atmospheric, ionospheric, lithospheric coupling that joins Earth to its cosmic environment. Our planet is not isolated. It breathes with the sun, hums with the magnetosphere, shifts with the moon's pull, and occasionally listens to the faint signatures of visitors from beyond the solar system. Each system influences the others through pathways still poorly mapped, governed by non-linear effects that resist simple modelling. In this sense, 2025 served as a reminder that Earth is not merely a rock orbiting a star. It is a node in a dynamic cosmic network sensitive to forces at scales both immense and subtle. Yet the most profound effect of the year may not be scientific at all. Instead, it may lie in the collective shift of perspective, an expansion of imagination grounded in data, uncertainty, and humility. The interstellar visitor 3I Atlas forced us to confront the limits of our knowledge. Its massive coma, its unexpected activity, its alien chemistry, all of it spoke to the vast diversity of processes occurring beyond our solar system. The sun's intensified activity reminded us that our world is shaped daily by forces that predate humanity and will outlast it. And the earthquake sequences emphasized with sobering clarity that our planet's internal dynamics remain powerful, unpredictable, and indifferent to human timelines. In the end, Part 13 is not about proving cosmic relationships or dismissing them, but about acknowledging the value of dwelling in the unknown. Science advances through questions, not certainty. And in this moment of convergence, the universe seemed to whisper a reminder that some mysteries are meant to stretch our imagination rather than resolve it. That wonder itself is an essential part of scientific inquiry, and that humanity, fragile yet curious, stands at the threshold of a larger cosmic understanding, not because the universe has changed, but because we are finally learning how to look. As this extraordinary sequence of cosmic and terrestrial events draws to a close, we're left with a quiet lesson that does not shout, but hums beneath everything we've observed. The universe is not obligated to reveal meaning, yet it never stops offering opportunities to look deeper. The earthquakes that rippled through Kamchatka, the geomagnetic storms that brushed across our magnetosphere, the immense carbon dioxide coma of 3I Atlas unfolding like a pale lantern around an alien core, all of them reminded us that Earth is not an isolated world, but a participant in a much larger and more intricate system than our ancestors ever imagined. None of these events demand supernatural interpretation. They sit comfortably within the domain of science, governed by physics we can measure and equations we can test. And yet when they align in the same season, in the same narrow passage of time, something in the human mind awakens. We begin to sense patterns not because they are proven, but because the cosmos in all its vast indifference is still capable of inspiring wonder, powerful enough to reshape how we think. Solar cycle 25 will subside. The comet swarm will drift outward and dissolve into interplanetary dust. Earth's fault lines will continue their slow grinding ballet beneath our feet. But the questions raised during this convergence will linger questions about electromagnetic coupling, about interstellar chemistry, about the hidden architecture of planetary stress. These mysteries will not resolve quickly, and perhaps they are not meant to. Their purpose is not to answer, but to expand. In the end, the real transformation was not in the sky or the crust, but in us. We looked upward and inward at the same time. We measured the universe and were measured by it in return. And in the hush that follows the storm, we find ourselves a little more aware of our fragility, our curiosity, and our small but luminous place inside a cosmos that continues quietly, patiently to unfold. Traveller. As we reach the final moments of this journey, allow yourself to drift in the soft afterglow of everything we've witnessed tonight. Earthquakes rising like ancient memories from the deep crust. Solar winds sweeping across the magnetosphere and through Eye Atlas, that silent wanderer, unfolding its vast shimmering coma as if exhaling secrets from another star. None of it ends here. The science, the mystery, the unanswered questions, they continue humming beneath the surface of our world, quietly shaping the space we sleep in. What we explored together wasn't just a sequence of events, but a reminder that the universe is never still. Even in the quietest hours, particles race, magnetic fields breathe, and the Earth turns beneath constellations older than memory. And somehow, Traveller, you are part of this motion. Not separate from it, but woven into the same fabric, the same physics, the same story. Perhaps that is the gentlest truth hidden in all of this. We don't need every connection to be proven for wonder to exist. We don't need certainty to feel awe. It is enough to notice, enough to listen, enough to let the cosmos pass through us like a slow tide. As you close your eyes tonight, know that nothing in the universe is watching you with judgment. It simply moves, radiates, and remembers. And in that vastness, your small existence is still meaningful, still luminous, still heard.